This lecture will introduce some concepts of probability. Probability assigns a number between 0 and 1 to a given event. The number represents the likelihood of this event occurring. To assign a probability to an event, we need to conduct an experiment, which is a procedure to obtain outcomes, that is, the results of an experiment. Suppose you want to know the probability of obtaining exactly 7 heads from flipping a coin 10 times. You have to flip a coin 10 times and note down the number of heads you obtain. You then have to repeat this experiment multiple times, and each time you get one of the 11 outcomes, you have to write it down. If you conduct the experiment, say 1,000 times, and 117 times the outcome is exactly a 7, then you know the probability of obtaining 7 heads from flipping a coin 10 times is around 11.7%. Before we will look at the details of obtaining a probability distribution like the one just described, we need to have some understanding about the theoretical aspects of probability. And this is what this lecture is about. So, to start, let us define some basic concepts of probability. The first concept I would like to talk about is what is called a sample space. A sample space is simply a list of all the possible outcomes of an experiment. And the notation for a sample space is the Greek letter omega. Now, here are some examples of a sample space. Think about rolling a die. Then the sample space is a list of all the possible outcomes. Well, if you roll a die, the possible outcomes is any number between 1 and 6. The same is true if you flip a coin. There, you can either get heads or you can get tails. Think about your grades in this class or any other class you are taking. If you think about that those grades may be uncertain to a certain degree, and it can be either an A+, an A minus, B+, and so on, all the way to an F. The same is true if you're looking at the number of fire station calls within a 24-hour period. I think about this as the number of 911 calls to a fire station. It can be either 0 calls, 1 call, 2 calls, and so on. Now, what about tomorrow's temperature? Well, we will see that we do not necessarily need to restrict the sample space of tomorrow's temperature for the temperatures that you think are going to happen, but we can simply make this very large of all the possible temperatures. And what we do when we assign a probability to the outcomes is that extreme cold or extreme heat is simply going to have assigned a very small probability. The next concept that I would like to introduce is the concept of an event. Think about an event as a subset of the sample space. For example, if you're rolling a die and you are interested in the event of getting an even number, then the elements in the event are 2, 4, and 6. Think again, you're rolling a die and you're interested in a number less or equal to 4, then that event, we call it S here on the slides, contains the elements 1, 2, 3, and 4. Suppose that you're interested in the number of calls to a fire station, and suppose that you have 4 fire trucks in your fire station, and you're interested in the event of getting 5 or more calls. Because if you get 5 or more calls, then those 4 fire trucks may not be sufficient. Then, in this case, the event F contains the elements 5, 6, and so on. Now, to visualize the concept of sample space, events, subsets, we can use Venn diagrams. Now, before we use Venn diagrams, we need to define certain set notation as well as set operations. The set notations and the set operations that I would like to talk about are what are called intersections, empty or null sets, unions, and complements. Now, let us first consider intersections and unions. Now, think when you're doing a Google search and you're looking for the term Indianapolis and motor speedway. Then when you're typing into the Google search Indianapolis and motor speedway, then you're looking for an intersection. In a sense, you're looking for web pages that contain both words Indianapolis and motor speedway. That is an intersection. If you are searching instead for Indianapolis or motor speedway, then you're searching for a union. You're looking for all the web pages that contain the word Indianapolis. You're getting all the results where the web page contains motor speedway, and you're getting the results of web pages that contain both words. That is an example of a union. Now, if you're looking for a term that doesn't exist, then you're getting a null set or an empty set. Okay? Note that an empty set or a null set is very different from a set that contains the number 0 or that contains a 0. Okay? So, for example, if you're considering odd numbers and even numbers, and you are looking for the intersection of odd and even numbers, then that set does not contain any elements. The last concept is called complements. The complement of a set X is the set of elements of the universal set that are not elements of X, and it is written XC. So think about rolling a die. Then even numbers are 2, 4, and 6. Then the complement of that set, of that even number set, are all the odd numbers. Okay? Now let us look at some set operations, and we are going to use Venn diagrams for this. Okay, so consider the example from the lecture notes where we are going to roll a die. The set or the sample space of all possible outcomes can be represented as a box where we can roll a 1, a 2, a 3, 4, 5, or 6. Note that the entire box represents the sample space. Now let us consider two sets, set E, which contains the elements 2, 4, and 6, and set S, which contains the elements 1, 2, 3, and 4. Now, set E, let's use green for this, is 2, 4, and 6. And set S is 1, 2, 3, and 4. So if we want to calculate the union, so the union of set E and S, then we get the elements that are in either E or S or both. So that would be 1, 2, 3, 4, and 6. And if we calculate the intersection, then that would only be the elements that are appearing in both sets. And that would be 2 and 4. Now let us define a new set called F, and let F be the union of E and S. So this is what we have calculated here. Now note then that F, the complement of this set, is going to have one element, and that element is going to be 5. Now, when you are working with probabilities, you have to remember that a probability of an event is a non-negative number. That is, it is bigger than 0 and it has to be smaller than 1. You can never find a probability that is negative or that is bigger than 1. Also, all the probabilities of the outcomes in the sample space sum up to 1. Think about you are flipping a coin, then the probability of heads is 50%, the probability of tails is 50%. Those are the two outcomes and they sum up to 1. The same is true if you're rolling a coin, then the outcomes are 1 through 6, each with a probability of 1 over 6, and hence, yet again, you have the probability that sums up to 1 across the entire sample space. Now, think about you're flipping a coin 3 times. Then the 8 events that can happen is either you get heads on the first flip, heads on the second flip, and heads on the third flip. This is what I marked with E1 on this slide. Now, the probability of each event is equally likely, that is, it's 1 over 8. And hence, if you're, for example, interested in an event where you get exactly 2 heads, you will see that you get 2 heads for the events E2, E3, and E5. So to find the probability of getting exactly 2 heads, you can simply sum up those probabilities. And you will see that the probability of getting exactly 2 heads from a coin flip, from a 3-time coin flip, that probability is equal to 3/8. Note that we can also use a probability tree to illustrate the concept of flipping a coin 3 times. What I have represented here is a probability tree, where we have the 3 coin flips, first, second, and third flip, and every time you flip a coin, you can obtain either heads or tails, and the probability is 1/2. Note that for a probability tree, the probabilities have to sum up to 1 for each level. Okay? If you are thinking about the event of interest before, that event was the probability of getting heads twice when flipping a coin 3 times. Okay? So we can see that to obtain heads twice, you either obtain it first flip and the second flip, and then you are obtaining tails in the last flip, or you're getting heads in the first flip, tails in the second flip, and then heads again in the last flip, or if you are obtaining tails in the first flip, then you have to obtain heads in the last 2 flips. So basically there are 3 paths for obtaining exactly 2 heads. Now, if you are going down a particular path in a probability tree, you are multiplying the probabilities. So obtaining heads, tails is 1/2 times 1/2 times 1/2, which of course is equal to 1 over 8. This is what we have seen before. But note that we have 3 paths where you are getting 2 heads, and you have to add the different paths to get the probability. So each path has a probability of 1/8. There are 3 paths for obtaining 2 heads, and hence it is 1 over 8 plus 1 over 8 plus 1 over 8, which is 3/8. This is an alternative way of calculating probabilities. Now, the next concept we are going to look at is called the probability of a union. And to understand the concept, it is easiest to illustrate it with a Venn diagram. We are also going to work through a couple of examples that involves alcohol and cocaine consumption, random safety checks by the police, as well as on-time arrival of airplanes. For the first example, when we are looking at alcohol and cocaine consumption, consider the blood content of randomly selected people. And again, note that the probabilities that I'm about to present are made up numbers and do not represent reality. Now define the following events. We have alcohol in the blood system of a person. We define that as event A. We define finding cocaine as event B, and finding both alcohol and cocaine as the intersection between A and B. The probabilities are as follows. The probability of finding alcohol is 86%, the probability of finding cocaine is 35%, and the intersection is 29%. That means 29% of people have both substances in their blood. If you want to find the probability that a person has either substance or both in their system, then you have to perform the following calculations. Now, if you find this example intriguing, then you should check out the following EU project. The justification for this alcohol and cocaine example is a project from the European Union which traces drug consumption in sewage water. What they do, and you can click here on this interactive tool, is that they are tracing various drugs in large cities in the European Union over multiple days throughout the week and also over multiple years. So for example, you can click on this map-based tool, and what you see is the cocaine consumption in various European cities. Note that you can look for cocaine, amphetamine, meth, ecstasy, and you can also differentiate between weekday and weekend. And you can also explore the daily patterns. And of course, you can also explore the yearly patterns. So for example, if you click on ecstasy, then you see that Amsterdam has by far the highest concentration ecstasy usage compared to every other city. You can also look of whether the consumption during the weekend or during the weekday is different. And you can see that from most cities, for example, the weekday consumption of ecstasy is much smaller, except for Amsterdam. You can also look at meth consumption, for example, and you can see that there's almost no meth consumed in Amsterdam, but that you have, for example, Prague or Dresden in Germany being high consumers of meth. Okay? So this is a justification for this study or for this question about alcohol and cocaine consumption. Note that certain drugs like heroin cannot be traced in sewage water. The second example about the probability of a union is we have safety checks by the police. Think about highway patrols randomly checking for the safety of trucks, and assume that they're interested in faulty brakes and bad tires, or a combination of both. Then if the probability of having faulty brakes is 23%, the probability of bad tires is 24%, and we know that some trucks have both problems. If that is 29%, we can actually calculate the probability that if we are pulling over a random truck, we can calculate the probability that this truck has faulty brakes, bad tires, or both problems. The last example that we are going to talk about is on-time arrival of airplanes. Note that if the events are mutually exclusive means that the events cannot happen at the same time, then the intersection between the events is always going to be 0. So consider the 3 events A, B, and C, and those are the arrival of airplanes that are less than 10 minutes early, which is event A. Within plus or minus 10 minutes arrival at the gate is event B, and more than 10 minutes late is event C. Now here, if you want to know the probability that an airplane is not arriving on time at the gate, not arriving on time at the gate means that it is either too late or too early, then you can simply sum up the probabilities of 0.2 and 0.36, and you get the probability of 0.56 that an airplane is not on time. To calculate the probability that events A and B occur, you have to use the multiplication rule or the probability of an intersection. Now, it is very important to realize that the rule is only valid for independent events. To calculate the probability that events A and B occur, you have to use the probability of an intersection or the multiplication rule. Now, it is very important to realize that the rule, the probability of A times the probability of B to get the intersection, is only valid if both events are independent. We are going to consider dependent events a little bit later on. For example, suppose you're interested in the probability of getting a 6 on the first roll when rolling a die, and a 6 on the second roll as well. Note that those events are independent in the sense that what you get on the first roll is independent of what you get on the second roll and vice versa. Now, the probability of getting a 6 on the first roll is 1 over 6. The probability of getting a 6 on the second roll is also 1 over 6. So if you are interested in the event 6 on the first roll and 6 on the second roll, you are simply multiplying both numbers, and you see that the probability of getting a 6 in both rolls is 1 over 36. We have introduced a probability tree in the past, and now let us apply a probability tree again to calculate the probability of getting a 6 during 2 consecutive die rolls. Now, you have your first roll, and now note that theoretically what you could do is you could draw a branch for each possible outcome, but since we are only interested in getting a 6 versus not getting a 6, we are only drawing 2 branches, where we say we have a 6 here and we have no 6 here. And of course, the probability of getting a 6 on a die roll is 1 over 6, and rolling anything else is 5 over 6. The same is true for the second roll. And again, we have the probability of 1 over 6 and 5 over 6 for rolling a 6 and no 6. And you can now calculate the probability of rolling a 6 on the first roll and a 6 on the second roll. And that probability would be is one path. You're multiplying if you're going down a path, is 1 over 6 times 1 over 6, and hence is 1 over 36. Now, the second example is about drawing cards. Suppose you have the event A, which is drawing a heart, and the event B is drawing a queen. The joint probability is the likelihood of drawing the queen of hearts and can be summarized as follows. The probability of drawing a heart is 1 over 4. The probability of drawing a queen is 4 over 52. And hence, the probability of drawing the queen of hearts is the multiplication of 1 over 4 times 4 over 52. And you see that since there's only one queen of hearts in this set, the probability is 1 over 52. Note that for the multiplication rule to hold, the two events must be independent. Now, if we are talking about two dependent events, and we are going to introduce this a little bit in more detail later, we have to slightly modify the equation. Now, suppose that you have 16 polo shirts in your closet with your company's logo on. 9 of them are green polo shirts and 7 of them are blue polo shirts. In the morning, you get dressed when it is dark, and you randomly grab a shirt 2 days in a row, and you're not doing the laundry within those 2 days. Now, when you're grabbing those polo shirts in the dark, you do not see whether you are grabbing a green or a blue shirt. Now, suppose that you're interested in a probability that you are actually grabbing 2 blue shirts in a row. Then this probability can be calculated as follows. Let us use a probability tree to illustrate the polo shirt problem graphically. So you have on Monday and Tuesday, and you have a total of 16 polo shirts in your closet, and in the morning you get up and you grab one shirt at random in the dark, and you do not see whether you are having a blue shirt or a green shirt. You are having 7 blue shirts and you have 9 green shirts, so you have a total of 16 polo shirts. So on Monday, the first day, you are having a probability of 7/16 to grab a blue shirt and of 9/16 to grab a green shirt. Okay? Now note that the second day, on Tuesday, there is a slight difference in probability. When you pulled out a blue shirt on Monday, then the probability of pulling out the blue shirt on the second day is now 6/15, because you only have 15 shirts left and one blue shirt is gone. Whereas if you pulled out a green shirt on Monday, then your probability of getting a blue shirt on Tuesday is 7/15. The same calculations can be made if you pulled out a blue shirt on Monday, then your probability of pulling out a green shirt on Tuesday is 9/15. And if you pulled out a green shirt on Monday, then pulling out another green shirt on Tuesday is now 8/15. And again, note that the probabilities are summing up to 1. 7 plus 9 is 16. And 6/15 plus 9/15 is equal to 1. And the same is true here. So now you can calculate the probability of pulling out 2 blue shirts on 2 consecutive days. And that would be 7/16 times 6/15. And that is the probability of pulling out 2 blue shirts in a row. Now, when we were talking about the polo shirts before, we have already introduced the concept of conditional probability. Conditional probability of an event A is that what is the probability of event A happening when we know event B happened? So for example, you could think about the probability of a person earning $150,000 or more after graduating law school. Or you could consider that probability is different from the probability of a person earning more than $150,000 per year, given the graduation from Harvard Law School. Think about the probability of a person getting arrested is different from the probability of a person getting arrested who had already a prior arrest. At the beginning of this lecture, we talked about the uncertainty in your grades. Now think about the probability of getting an A in graduate statistics is different than the probability of getting an A in graduate statistics, given that your undergraduate degree was in mathematics. Okay? So the conditional probability basically restricts the sample space only to a certain subset of events. For example, the probability of rolling a 2 with a die is different than the probability of rolling a 2 given that you know that you have rolled an even number. Now, let us do an example about good and bad service. Think about you are about to hire a plumber, and you know that the plumbers in your area either provide good service or they provide bad service. And you also know that some of the plumbers have been in business for more than 10 years, and some of the plumbers have been in business below 10 years. We are going to answer 2 questions. The first question is, what is the probability of receiving good service? And then we are going to answer the question, what is the probability of receiving good service given more than 10 years of experience? Now, let us consider the problem with the plumber. We said that there are 50 plumbers in town and that some of them are providing good service, some of them are providing bad service, and that some of them are in business for more than 10 years and some are in business for less than 10 years. Okay? Now, again, note that we are picking a plumber at random. Okay? So if we are interested in the probability of getting good service, given that the plumber has been in business for more than 10 years, then we have to calculate the probability as follows. We have to calculate the probability that we are receiving good service in those that have been in business for more than 10 years. Divided by the probability of getting a plumber who has been in business for more than 10 years. Okay. Now, the probability of getting a plumber that has been in business for more than 10 years is 20 over 50. And the probability of getting a good plumber and who has been in business for more than 10 years that probability is equal to 16 over 50. So the probability of getting a good plumber who has been probability of getting a good plumber knowing that that person has been in business for more than 10 years is equal to 16 over 50 divided by 20 over 50. And hence that probability is, that conditional probability is 16 over 20. Now let us look at the concept of independence. Two events, A and B, are independent if knowledge of B does not affect the probability of A, and vice versa. Now let us consider two examples here. Think about you're rolling a red die and you're rolling a green die. Let event A be the 4 on the red die, and event B, the sum of the dice is odd. Now the question is, are A and B independent? Let us consider this example visually, and you have all the information you need in table 2 on the next slide. Now let us look at the concept of independence, and we are going over example 1, where we are rolling a red die and a green die. Event A is getting a 4 on the red die, and you can see that the 6 elements where you have a 4 on the red die are already marked. So if we call this event event A, then the probability of event A is equal to 6 over 36. Event B is that the sum of the dice is odd. Now note that 50% of the 36 outcomes is where the sum of the dice is odd, and hence the probability of event B is equal to 18 over 36. To calculate independence, what we have to show is the following. We have to show that the probability of A, given that B happened, and we can use the definition of the conditional probability here. We have to show independence. We have to show that this is equal to simply the probability of A. Okay? And so this is what we are interested in. So I put a question mark here. We know that the probability of A is 6 over 36. And we know that the probability of event B, that the sum of the dice is odd, is 18 over 36. So what we need to know is the probability of A intersection B. That probability is where the sum of the dice is odd and there is a 4 on the red die. So there are only 3 elements out of the 36 where that intersection is true. And now when you are doing the calculation, you can actually show that the 2 events are independent. Why? Because you have 3 over 36 divided by the probability of B divided by 18 over 36 is equal to 1 over 6. So the probability of A given event B is 1 over 6, which is exactly the probability of A, 6 over 36. Of course, 6 over 36 is equal to 1/6. Hence, both events are independent. Now, in the second example, let us define event C as at least 3 dots on the die and event D as the sum of the dice equal to 7. Again, we are interested in are C and D independent. And let us consider the information in table 3 to find out. Let us look at example 2, where we are now going to present a result where we have 2 dependent events. Event C is having at least 3 dots on either die. And note that this is true for all the outcomes except those 4. Okay? Here, for those 4 outcomes, we do not have 3 on either die. So the probability of C having at least 3 dots on either die is 32 over 36. The probability of event D, which is the sum is equal to 7, which are those 6 elements. The probability of that event is equal to 1 over 6. Now let us calculate the probability of C given that D happened, and we know that this is equal to that the conditional probability is the probability of the intersection of C and D divided by the probability of D. We know that the probability of the intersection are all the elements that where it sums up to 7 and where there are at least 3 dots. Note that that probability is equal to 6 over 36. Because we are looking at those 6 elements. So now we can calculate the conditional probability of C given D, which is equal to 6 over 36 divided by the probability of D, which is 1 over 6. And hence that probability is equal to 1. Thus the conditional probability of C, given that the D happened, is not the same as the probability of C, and hence we are looking at two dependent events. In order to explain the law of total probability and Bayes' rules, we are going to use a probability tree. But here's the story. Think about a fire alarm. If you hear a fire alarm in the building, all you know is that there is a fire alarm, but you do not know whether there is actually a fire or not. The same is true for any type of medical test where you get either a positive or a negative result. Then you do not know if you really have the medical condition or not. There's either going to be a false positive or a false negative. In this case, we are going to explain the topic of the false negative and false positive as a test for mad cow disease, okay, or BSE. Now, here we have the problem as follows. Okay, let us illustrate the concept with mad cow disease. BSE is mad cow disease, so that a cow actually has BSE, there's a 2% chance, and there is a 98% chance that the cow does not have mad cow disease. If the cow has BSE, then a positive test result, there's a 70% chance of that happening. And if the cow does not have BSE, then the test result being negative, there is a 30% chance. On the other hand, if the cow does not have BSE, the probability of a positive test result is 10%, and the probability of a negative test result is 90%. Note that the cow having BSE and a positive test result is correct. The same is true for the cow not having BSE and a negative test result. Now, the question is, what is the probability of a positive test result? Note that there are two instances where the test result is positive. That is, if the cow has indeed BSE and if the cow does not have BSE. So when we are observing a positive test result, all that we are observing is that one of those two paths has been chosen. So to calculate the probability of a positive test result, we have to multiply down the path and then add the path. So we have to do 0.02 times 0.7 plus 0.98 times 0.1, and that is equal to 0.112. So there is an 11.2% chance of a positive test result. Now, if we are interested in the conditional probability, that what is the probability of the cow having BSE or the cow having mad cow disease, given that we have a positive test result, then we have to proceed as follows. What you have to realize here is that if we observe a positive test result, then we know that we are either here or here. The same is true that if you think about this example as a fire alarm, where there can either be a fire or no fire, and there can be a fire alarm and no fire alarm. When you hear the fire alarm, all you know is that there is a fire alarm, but you do not know whether there is a actual fire going on or not. The same is true in this case, where we have a positive test result, but we do not know whether the cow actually has BSE. To proceed in calculating the probability of the cow actually having BSE, given that we have a positive test result, we have to proceed as follows. we have to multiply the 0.02 times 0.7. So this is the event that we actually have BSE and a positive test result, divided by BSE having a positive test result plus no BSE and having a positive test result. And we have calculated this before as 0.112. And hence the probability of the cow actually having BSE, if there is a positive test result, is 0.125 or 12.5%. The last topic we are going to cover in this lecture about probability theory are combinatorial methods. In particular, we are going to talk about permutations and combinations. Permutations and combinations is a way of counting how many arrangements there are if you pick a set number of objects from a total set of larger objects. So for example, if you consider a bowl that contains 6 balls with the letters A, B, C, D, E, and F, then permutations and combinations allows you to say if you are picking 2 balls from that set of 6 balls, how many different arrangements do you have? The difference between permutations and combinations is that for permutations, the position matters. So A and B is different from B and A. Whereas for combinations, A and B is the same as B and A. In this case, with the 6 balls, think about you are having 6 balls and you pick 2 of them. Then, based on the equation presented on your slides, there are 30 different arrangements of those 2 balls taken out of the 6 balls. Combinations also count the number of different arrangements, but in this case the position does not matter, in the sense that A and B is the same as B and A. So given the example before, where we had with permutations, if we picked 2 objects out of the 6, we had a total number of 30 arrangements. Then with combinations, we only have an arrangement of 15. And let us illustrate this again with a different example. Let us now look at the difference between permutations and combinations. Permutations is the arrangement of object where the position matters. So as an aid to remember whether the position matters or not, think about P, position, and permutation starts with a P as well. In combinations, the position does not matter. So let me illustrate this with a couple of pens. So we have a green pen, a black pen, a blue pen, and a red pen. Okay? Now, we have 4 pens, which is the total number of objects that we have, and K is going to represent of how many objects we are actually going to pick. So think about N is equal to 4, and let K be equal to 2. So permutation lists all the number of arrangements that are ordered. So if I have 4 objects and I pick 2, then green and red is one possibility. But note, since the combination matters, we have red and green as one arrangement, and green and red is a second arrangement. We will see that with combinations, green and red is the same as red and green. To calculate the number of all possible arrangements with permutations, let's assume that we have N equal to 4 and K equals to 2. So n is equal to 4, so we write 4 factorial divided by 4 minus 2 factorial, and hence we see that there are 12 arrangements. With combinations, the ordering does not matter. Again, green and red is the same as red and green. For combinations, assume again that we have n being 4 and k equal to 2. Then the equation that we have to use is similar to the permutations, but we have to divide by k factorial. So we have 4 factorial divided by 2 factorial times 4 minus 2 factorial. In this case, we have 6 possible arrangements. Note that it is only coincidence that in this example that we have half the number of arrangements. We will see that combinations is going to play a very important role when we are going to look at the binomial distribution.